We'll start by going through the motivation behind creating this project. Then we'll talk about the hardware requirements, problem statement, objectives, and assumptions before starting the project. Finally, we shall talk about the agent, the modules we have used, the workflow of the agent and the LLM, and our working video. To conclude, we'll present our learnings, our contributions towards the project, and future work that could be created on the basis of this model. Then we would like to thank the references that we have taken to complete this project. When we started looking for potential topics for this project, we figured out a landmine detector is a very useful robot. We used and read the article that has been mentioned in this particular slide, and we realized how a landmine detector is just an exaggerated, scaled up version of a metal detector. So we decided to make a metal detector which would be all purpose and not particular like a landmine detector. This was the motivation behind creating this project.
Now let's start by going over the hardware requirements for the project. To build our metal detection robot, we use several key components. An Arduino board as the main controller, chassis and wheels to form the body and allow movement, motors for driving the wheels, a battery pack to power the robot, metal detecting circuit consisting of inductive proximity sensor for metal detection, IR sensors for following the path, and a camera to record the robot's movement and send data to an AI model running on a laptop via a Python script. These components together helped us create a working bot that can follow a path and detect metal objects.
Our problem statement is quite straightforward. It is to build a robot that follows a dark path against a light background and detects presence of metal on its path. So we want a robot that will not only traverse the entire path but will also alert us to the presence of any metal on its way. Our objectives following our problem statement were to devise and construct a robot that not only traverses a given path but also gives confirmation when any object that contains ferrous metals is encountered. As you can see in the slide, our final model is affectionately named Shanky after the first general purpose mobile robot, which was called Shaky.
The assumptions of our project are that the robot's environment is a black path against a white surface. The robot will surpass the metal objects placed in between. On failing to do so, the objects will be removed manually. The entire procedure will be recorded on camera, and this video will be fed to the LLM using a Python script which was explained later in the video. Our agent is a goal-based agent where the goal is basically to detect the presence of the metal on the predefined path. Describing the PAS of this problem statement, the performance will be judged based on the accuracy of metal detection, and the robot is expected to follow the correct path. The environment, as described earlier, is a dark path against a white surface with various metal objects in between. The actuators are motors, LEDs, and buses, and the sensors are the IR sensor used for path detection and the metal detection module used for metal detection.
Next, let's talk about the AI modules we used from our course. We used two specific modules in this project. Module 2, Automated Problem Solving Agent, which follows a goal-based approach. The goal in our case was to detect metal while following a path. The robot uses sensor inputs like the metal detector to help make decisions along the way. And Module 5, Robot Motion Planning, which focuses on the robot's movement. The robot uses IR sensors to follow the predefined path and adjust its direction to stay on track. These modules helped us design the robot's behavior step by step to meet the specific goals using sensor data.
So moving on to the workflow of our project, the first thing that comes is the environment. The physical environment of the bot consists of a dark path against a light background, and there are various metal objects which are scattered all along the obstacle path of the bot. Then comes the perception. We have used two different types of sensors. One, the IR sensors, which are mainly used for mobility, and the metal detecting module, which senses metal objects. Next, the bot has been modeled such that it senses whether the path it is moving on is black or white. On that basis, its behavior is that if the path is dark, it keeps moving. That is, it keeps following the line. Else, if it detects a white background, it stops. The motion of the bot is such that it can turn left, right, it can move forward, and it can stop. It can also handle sharp turns and U-turns. The metal detecting module either beeps when it senses a metal or it doesn't. Next, the controller is Arduino Uno, which is the brain of our project. It receives the inputs which are given by the sensors, and on that basis, it provides output signals to the actuators, which are motors, which in turn control the wheels. So, the motion of the bot is controlled by Arduino Uno. And this process is repeated till the entire obstacle path is followed and it is completed.
Since we have used LLM to analyze the video and understand what metals exactly the robot has encountered, we first need to understand how to give input to LLM. Normally, we can give input to an LLM using their front end, that is their website, or we can use an API key. We have used API key for Gemini 1.5 Flash, for which we are very thankful to Gemini. The API works similar to how we access a website from our computer. First, we use a Python script which already contains the API key in a variable, and it takes the video as well as the prompt that we wish to give to the LLM as input. This user input is then given to Gemini through the Python script. That is, it is the script that sends the request and sends the input alongside with it. The script also has to tell Gemini what kind of input it is sending, so Gemini can understand what it is receiving and what it is to send back. Then Gemini 1.5 will process the request and will process the video along with the text that it has been sent as a prompt. Finally, using its models, it will generate some output which will mostly be a text-based answer, and this text-based answer is returned to the Python script which presents it back to the user, that is us. Now we come to the fun part. Exactly how does the LLM work on the video? This is actually a 7-step process and it is quite fascinating. The first step is very basic. Since we sent the video and the text prompt through an API request, our model first needs to extract this video and text. So this is what is done in the first step. It decodes the request and it extracts the video as well as the prompt. Now it cannot work on the entire video. Instead, it will take some stills from the video. In this context, stills means the video at any given particular time, which could be every 3 seconds or every 5 seconds, etc. Since this video also contains audio data, these stills are actually going to be an image plus some audio. These may be chosen at random intervals also, but generally it goes for systematic intervals. Then we come to step 2, which is visual feature extraction. Here the model will use an algorithm so it can analyze the features of the image. For example, it may try to identify objects or their surroundings or how far or near two objects are placed to each other. Step 3 is similar, but this is done for audio data instead of visual data. Then we come to step 4, which is where the magic happens. The model has already extracted the stills, it has identified objects. Now it wants to find some relationship between these different frames and the objects that it sees in all of these different frames. So it will map the change in the frames that it has chosen. For example, it may see that at t is equal to 0, the bot was at a certain position, and at t is equal to 3, when it took the next still, the bot had moved. So now it knows that the bot is moving because it has changed positions. It also knows that there are certain objects in the background that are not moving because they are still there and they have not changed position at all. It will do this for almost every prominent object that it identified in step 2 and step 3. Since our model was fed a video that is a mixture of visual as well as auditory data, it had to use 2 different models to process them. Now that it has gotten an output from both of these models, it needs to incorporate them together to come to a better logical conclusion. This happens in step 5, that is multi-model fusion. In step 6, which is knowledge integration and reasoning, the model now uses its training data and the newly acquired information to finally come to an answer that it can give back to the Python script that had sent the API request. In step 7, whatever information or answer that the model has decided on in step 6 is converted to natural language, text based, and it is sent back to the Python script which had sent the original API request.
As it can be seen, the robot moves along a black line against a white background and also detects metal objects along its way. Please note that the slight beeping that occurs all throughout the video is because the metal detecting sensor also detects its own metallic components to some extent. However, the beeping becomes significant when it detects a metal obstacle, in this case, a smartphone.
As we can see in the image, this is the input that was given to the LLM, and the second image is the output generated by it. It describes the video and it also tells us exactly why the robot stopped. So it not only describes the video but also tries to analyze the actions of the video with respect to everything else in its surroundings. I would now like to discuss my contributions to this project and the learnings that I gained from them. I was tasked with finding the right LLM and getting the correct API key, as well as writing the Python script that would generate the API request and print the output. I tried all the LLMs that were listed on this page, but I finally chose Gemini because Gemini 1.5 Flash, that is free for a limited number of queries. It allows image and video input and it gives quite accurate outputs. I worked very little on the hardware, but mainly alongside the metal detecting module and its calibration. My best contribution, however, was figuring out how to stop the metal detecting module from detecting the metal in the bot itself. I did so by placing a cardboard parallel to the bot on top of it, such that the metal detecting module is far enough from the circuitry to detect the change in EMF, but yet still arranged such that it will move with the bot. I have also learned that theory is not very helpful while dealing with hardware because it is very unpredictable. You may get the perfect output while you're using the simulation, but when you try to use it in actual practical situations, your hardware just gives up on you. But the most important learning that I have drawn from this project is that AI is not limited to LLMs. AI is everywhere. As I have been learning throughout the course, anything that can make a decision upon receiving some percepts is AI. So I think I have learned a lot from this project.
My contributions in this project include working mainly on the hardware setup. I contributed in assembling and connecting the various components of the robot. I also learned how to use Tinkercad to simulate and test the circuit before building it physically, which helped us identify and fix issues early. Additionally, I also researched microcontrollers like the ESP32 to understand their features and see if they could be used as an alternative. Through this project, I gained experience in integrating hardware and software and how important simulation tools are for quick prototyping and testing.
My contribution and learning in this project are I learned basic Arduino coding and was also introduced to Tinkercad, where I simulated basic Arduino circuits before diving into the real deal. Though not implemented in this project, I spent a good chunk of time researching on ESP32, its pin diagrams, how many pins are available to us if we use the CAM module or the SD card module. This helped us to check the technical feasibility of using ESP32. Since LLMs are implemented in our project, I explored various LLMs, for example, Llama on Hugging Face, and checked its accuracy by giving it various inputs. Additionally, I also learned basic skills like video editing, audio editing, etc. My biggest takeaway was to how important it is to accurately represent the problem statement, that is problem representation, and also how important it is to check the technical feasibility of the various solutions we come up with.
Talking about my contributions and what I learned from this project, I was mainly involved with the hardware components. I spent a lot of time searching for the best and cheapest hardware components. During the first phase of the project, before actually making the bot, I learned how to build and simulate circuits on Tinkercad. I also found many creative solutions while making the bot. Due to the absence of a multimeter, I ended up making a makeshift voltage detector using breadboard, LED, and resistors. I also figured out how to mount metal detector and also dealt with burnt wires. I was also involved with the programming of Arduino Uno, the calibration of sensors, and the overall assembly of the robot. Through this project, I learned that an engineer is a person with a never say die attitude, and we should always keep coming up with solutions till we reach the goal.
For our future plan, we aim to give our robot capability to move onto open ground, identify obstacles, and traverse through complex environment, finding its own path. This is the news article link mentioned in the motivation slide, and the second link is a YouTube video we took reference from. Thank you.